capabilities that Margaret showed you, or the functional block diagrams, or advanced preventive maintenance planning, task modeling, and all those things. There are many different areas where you can get deeper and build specific capabilities in OPUS Suite, and those are called extended or feature training. So I think it's a good idea to build, to add that after some time. And if it's interesting with tactical optimization that we showed that case study of, that's also a good thing to add. So there, I think when you get to step 3, it's more flexible. We can always discuss what is most applicable based on your needs and the project and so on. Those can be tailored based on your needs. So I think just to say who should take what, I think that this type of course can really be all users that are new to OPUS Suite. It's really good to take this overview course. But it's not only for users, it's quite good for those who get the decision material as well. Managers and stakeholders and parts responsible and so on. It's good to get this overview of all the things that you can do with OPUS Suite to understand the power of this type of application and the big range of things that you can do with this decision support platform. Then I think it's good that all users, anybody who's really going to work with OPUS Suite, take those step 1 and step 2. Maybe if you're not doing so much cost modeling, you can skip that and so on, but otherwise, at least step 1, most should probably take step 2. And then typically we have a small group of expert users within each organization, and I think it's good for those at some point to take the extended course. And it's not only that you need to know all those things, it's also good that you build a confidence in getting into new areas. You know that OPUS Suite can do LoRa, but if you want to get into that and make big decisions based on that, it's really good to have the course as a basis to know how you should get started. So I think it's something for you to consider. You can always discuss with our colleagues at Systecon교육 Korea, and we're happy to set up those things when you think that it's good timing for you. So that was just my comment. Yeah.
We jump back to this screen. Recognize that. So now it's really last session, and I have a few more demonstrations that I'd like to share with you, some topics that we can work with. So I'm not going to dig too much in how to do it or on why we do it and what the outcome is. Okay, so Oscar mentioned FBD. I said it before, functional block diagrams, which is a way of handling redundancies in the systems. So I'll show you an example here that I've done. And I mean, for a standard, we're back at this sort of larger helicopter case that I showed you before as well, more real world, not just the engine system, but you see here all the subsystems. Okay, so as a standard assumption in OPUS Suite, we say that all items are in a series structure. So it means that as soon as one of them breaks, the system will stop. And that's not always the case, but especially in the world of simulation, it can be quite important to build different other types of functional configurations and block diagrams. But in terms of spare part optimization, you should always be cautious because redundancies are often there for extra security in the system. So you say that we have 2 of a certain subsystem, and that's for a reason. We have it because we want to be able to continue operating. But if you start, and then you might want to buy spare parts so that all of them are as available as possible. But if you start removing that possibility, you will also lower the reliability, because then you save money on those extra on those extra redundancies instead. So it's sort of a trade-off that's important to be aware of, and I just want to mention. With that said, I'm going to show you how to do it anyway in Opus here. So first of all, we can, if I click the view menu here, there is something called the FBD view. So that's another view that pops up here. So it's the functional block diagrams. And those are defined per variant. So if I select my helicopter variant here, you see that I see all the items here. The original case, they are just in a straight series, all of them. And you see all the these are the subsystem, the 51 engine, this one, the 3 landing gear system, this one, and so on. And behind, if I click the plus sign on the engine here, what happens is that it's going to be the exact same as we have here. It's the 511, 516, etc. All of them in a long series like this. Same thing for all the other subsystem as well. So that's the default behavior. But if I open up a file here where I've added some redundancies, and I click the variant again. So what did I, in this case, I said that, okay, so there are some redundancies here. And first of all, we have the item called 643. So I can look that up, just find it here. So it's from the communication system, and it's this item here. So when I click it, I changed the parent in the FPD, so I go back to the variant. Anyway, it's the 643 item, which we have 4 of. It's some part of the communication system. You can turn on the descriptions here again. Here, show descriptions in tree, that one, and then we get a better explanation of the different items are. Okay, so 643 here, so it was a power unit for the communication system. There are 4. And here I've modeled a parallel redundancy, as you see. That's what this block diagram shows. And I've defined that we need 3 out of 4 to be in operation. So it's enough that 3 of the power units are working and the communication system is still okay. And of course, this is input, so I can write 2 of 4 or 1 of 4 or whatever we want to have. So that's one type of redundancy that we can build here. So it's a standard K out of N redundancy built here. And then the other one is more, here I've created a series of 2 different items, which is, I don't know if you can read the numbers from those, but it says, that's number 649, and then it's 2 similar, which is 6414. So 649 here, it's the transmitter, and then there's a circuit, you see 6414 down here. And there are 2 transmitters and 4 circuits in total in this system. So what I did here is that I created a separate series for one of the transmitters and 2 of the circuits. And then there is a parallel relationship with another similar series. So this means that, and then, you see there it says 1 out of 2, if you can see that. So meaning that I need 1 of those series working. So either of, so I need 1, again, I need 1 transmitter and 2 circuits. That's what I want to say. Okay, so this is just an example on how you can build up the functional block diagrams. And now if I run both of those, remember we have a calculate all, so I run both of the cases, both the one without the FPD and the one with this FPD. So what would you expect from the results, which would be better in terms of cost effectiveness? With or without FPD? Oh, with FPD, I would assume, because we have now said that we don't need all the items operating at the same time. We can actually accept that some of the items sometimes fail and we can still be available with the system. And that's why we see the orange curve here with the square boxes. It's the one with where I added the FPD. Because you see that it's above the curve for the original case, meaning that we can reach higher availability for the same cost. And if we compare, I'm going to zoom a little bit in the graph here, let's say we go around 90%, So if we have a requirement of 90% availability, you see it will be the first point on the curve there, and on the other one, there, that one, so 90.2. So then we can use that diff functionality, and we see that it would be an increase of 4.5 million in this case in total life cycle cost. But as you see, it's not that many. It's not that many percent. This is a big case, so we are at 280 million. So a couple of percentage in increased costs for the one without FPD. And then, of course, it's interesting from a spare parts perspective to look at the differences in the stock size here. So if I click the result table view up here, and we're looking at the stock sizes, I'm gonna just summarize over all the stations, and then we can do some other fun stuff here. We can put the anchor, show the delta, and then I'll sort the deltas so we see where there is a difference. So you see here, for the original case, for the circuit 6414, originally OPUS then recommended 20, but with the FPD, with the redundancy on this, now the recommendation for the same availability is halved, so it's down to 10. So yeah, the difference is -10 here. And for the transmitter 649, you see that we go from 8 to 2, so that's decreased with 6. Same thing with the power unit as well, has also decreased. And then there is some other little bit change in the mixture as well, because it's a big scenario, so there seems to be some other small changes too. But those are the three main changes, and those are the three items that was included in the FPDs. So since they are not always critical for the operations, we can, it's enough to store less of those items. Of course, there are some details here. You can, in the input, you can say whether it's in operation all the time or not, or if, so typically when you have a redundancy, either not all of the subsystems are necessarily powered on. It can be that I'm actually only using 2 out of 4 transmitters or something like that. Then you can control that in the input too. And when it comes to so this is what we do with in the world of optimization and the steady state model. But in the simulation model, we, as always, the degrees of freedom are much larger, so we can build much more complex structures and handle more variations over time, etc., etc. But here's what that's still was an example on how to build an FPD. I have another thing here, and I wanted to show you from Simbox, or from the world of simulation. I mentioned it before, was the what we call the operational modes. Hope it's in this file. I think so. It's in the same. Just gonna double check so I have the right file here. Yeah. So in this scenario, I mentioned it before, the concept of operational modes. So it's really a way of defining different ways of operating the same system. And here I have 4 different ones. So one that I call basic flight, which is the standard way of operating the helicopter. We have something called air-to-ground capability, and we have something called reconnaissance, and something that's called fully equipped. And for each of those modes, here I've defined them. I have, these are my notes, just that's, so it's not actually meaning something. But what we do in the other table here for system operational modes, I can define for my helicopter. Here is just one variant, by the way. It's not with a night vision, so I have just one variant. It's called helicopter. And I have my 4 different operational modes. And then I use something that's called non-critical sets. So a non-critical set is a description of a set of items that are simply not critical at all for the operation. So in the case when I say that I'm operating fully equipped in that operational mode, fully equipped, I refer to the non-critical set that is called all critical. So that means that to be able to be in the mode fully equipped, then everything is critical. So I need all the items to be able to be available in order to operate in this mode. And then, so I can show you the non-critical sets here that define, and then they are connected to the different subsystems here. So, so if we take the one with everything, yeah, then everything is critical. But so it's sort of I called it critical sets, but or sorry, it's non-critical sets. So it's the items that are non-critical. So for the one that needs all items, there's nothing that is non-critical. I hope that makes sense. Anyway, so for the example, for this one, the non-critical, the basic ones that I used for the operational mode here, the basic flights. So for basic flights, it refers to the basic criticalities. So that one says that, okay, the FCS and the ECS and the CS are non-critical, meaning that the rest of them are critical. So I need the engine, I need the landing gear, I need the fuel system. So those three subsystems are critical to be. So that's the sort of the standard. That's what I need. And then maybe it doesn't really make sense here, but the flight control system and the environmental control system and the communication system can be out, but I can still not, sorry, it's not fuel control, it's flight control system. I guess you wouldn't fly in reality without the flight control system, but this was for demonstration purpose. So those three subsystems are non-critical if I'm operating in this mode. Same thing here for, and it continues like this. So here the basics and flight control systems are critical. The other two are non-critical. Same thing here. So, but what happens, what's kind of interesting now is that we can follow these different operational modes. This is a little bit technical to understand what's non-critical, etc. But it's important that we have 4 different operational modes, and we want to understand how ready are we to perform those different type of capabilities. So running the simulation here. Give us a result, and yeah, okay, so it says we have all the standard results here that we've looked at so far with the mission and system results and so on, but in the system results, just gonna turn off the percentage here, so we have 20 systems in total. Here I have something called system, and both mission operational mode and capability operational mode. So we can look at this one because that one's kind of interesting. So here I see for each of my operational modes how many of those of my 20 systems are ready to fly on a basic flight. And same thing, I can of course change here, switch to look at the air to ground or reconnaissance and so on. There you see the reconnaissance is far less because it requires more the systems, and to be fully equipped, it was about the same. And if I do it total here, I can see them all at the same time. If I select all parameters here, and you see that the basic flight and the air to ground, well, yeah, they seem to go pretty well, but when I want to do reconnaissance or go fully equipped, well, the probability is much. Well, I have less systems that are ready for that kind of operation. And what's important here is that those states or those operational modes are not only, it's not just showing what I'm doing on mission, because what I've been doing on mission has been that kind of result has been around for a long time in OPUS Suite, but this result that we're looking at here is really new, and the big difference is that we can get a picture of what we are ready for. So we are talking about actual readiness, no matter if we are on a mission or if we are at home or just waiting, we can still analyze how ready we are or how prepared we are to perform different type of missions. So there's a big difference. Normally we look only at the results while we are on mission, but here we look at what can we do in general, what are we prepared to do. So it's like an analysis of our fleet preparedness. Yeah, that one is a little bit complicated, but I think it's still interesting to show how it works. And of course, as always, we could have looked at the percentages, and so on. I had some other ideas on things some examples on typical questions that our customers has and how easy it actually is to work with them. So I'm just gonna use my Swedish notes here. So a classic question, if I have so let's say we have our have this, it's more the big case here, or the complex case as I call it. I'm just going to remove the FTD view. We don't need that one right now. Okay, so we have the original file here, and then a common question is, what happens if we fly with those helicopters some extra, like what if we increase the flight with 10%? So the planned flight hours per year is increased to 10%. What happens? What will it cost us, and how will it affect the readiness and availability? And that's a complicated question because there are a lot to it. But once we have the models, it's really not complicated to answer it. So I have this original case here, and we run it with a special optimization to get the cost effectiveness curve. And there's the first point with 90% availability with cost and so on. And then going back to the input, and if I save the file, file save as, and I call it helicopter plus 10% operations. Okay? And of course, I go to the table called, if you remember, utilization profile, which is the table where we define how many hours we're operating per year. And so 280, so that's around, say we go up to 300 hours, 150 would be 165 hours, and 280 is something like 300 and 300. So we're increasing the utilization, or maybe it's not for all of them, maybe the last one there, maybe even, we can do any small adjustments here as you want, but let's say that it was plus 10% on all of them. Yeah. Anyway, so you give any number you want here, and then we just press calculate, and it's a very small change, but it's a very interesting question. So what happens? Well, obviously, flying more hours will be more expensive. Why? Well, we can look at that, but so here, if we still have the requirement of 90% availability, so we have 90% here, and somewhere here. And in those, by the way, in those more real-world scenarios, complex cases, as you see, we can get very many points on the curve. So here we're looking at point number 570. So it's possible to get a lot of points on this curve. Of course, you can control that if you don't want to, if you of some reason want less points. Just to show you, so in the control parameters here, there is something called number of points. As you see, default value is 200, but you can turn that up as well. I can come back to why. But that's why we have so many points here, because I selected to show 1,000 points per curve. But anyway, back to the question here. So 90% there cost 300 million, and here 90% was 285 million. So using the difference there, we see that it's approximately an additional 15 million for this scenario, whatever zoomed out there. I don't know if it's 10 years or I don't actually remember exactly. A quick look at the global parameters. We're looking at a 20-year scenario here. So it's quite, I mean, we're repeating those for 20 years, so the costs are pretty high. But anyway, over those 20 years, the total cost increase of 10% additional flight hours will be 15 million approximately. And then we can, of course, dig deeper and see what the differences are in terms of spare parts or repair costs and so on. And that's, we can do it here, for example, in the result view, remove the difference, because we've been looking at item results here, but I can also look at, for example, system results. Click the one, okay, and then we see, here we're looking at mean downtime, for example. So it went from we have more spares, but okay. Anyway, the mean time between failure is the same. Yeah, of course, we didn't change the reliability, we changed the number of flight hours. So the mean time between failure is the same, but we have obviously the mean downtime has decreased, and that's probably because to reach the same availability, we need quicker repair times, because so we probably have more spares. That's why it's more expensive. We have more spares, but we also get more failures because we fly more hours. So even though the reliability is the same, mean time between failure is the same, but the number of flight hours has changed, so the number of repair actions has. We can see that here if we look at the number of demands per year. We see that. So the one on the right is the plus 10%, right? So we see that the demands per year has increased also. But if we want to look at the costs, I can select move demand per year instead of look at the recurring costs. And we see that it's that mainly the recurring cost that has increased here. Probably that's a big part of this. That's 3 million there. But if we look at, of course, next part here is the overall results, because this was, now we looked at item results, system results, but there's also something called overall results. And again, a lot of parameters available, but if we look at now, for example, the total investment in items and the recurring costs like this. There were others selected as well. Deselect them. So we can see how can move around the axis here, by the way. So the point on the case is on the same here. So we see for the original, the CI was 44.3 million, and for the plus 10%, so CI means total investment costs. So spares, investment, and resources, and whatever other things we need. So that's increasement, as well as the recurring cost here, as you see, which went from 241 to 253. So over those 20 years, it would be a total additional cost of approximately 22 million. So a lot of results to understand, but the only thing we did was to turn up number of operational hours, but we get all those results right away, and we can answer all those questions directly. Another example on something, on a question that is typically interesting. So what happens if we invest in spare parts given some assumptions that we did, and then we have those spare parts, and then it turns out that the reliability of the system is higher or lower than we expected from the beginning? How will that affect our cost effectiveness? And again, when we have the model ready, this is not a big task, even though it's a complicated question in the as it is. But we start with the same case again, same helicopter case, run the original scenario, right? Okay, and then we say again we can take this point here, 90% availability. It's point number 566, and then I can use this. If I right click here, I can do the insert allocation. Means that I can save this the spares and resource allocations that are optimized here. So I save it into this file. Click OK there. You see now if I go to the stock allocation table, and we had some points before, but here is number point 566 as you see. So we have that here. So I'm going to save it with a new name. I call it point 566. Okay. And what we want to do now with this case is to, as I said, the question was, if we've invested in those spare parts and, for example, the reliability change, what will the outcome be? So that means that I first of all want to lock. I don't want to do another optimization. I want to lock the calculation to this single point, this specific spare part that we've already bought. So if I go to the control parameters table, there is something called the problem type. We did this we did something similar. We're looking at the problem types here. So it says initial, which is the default value, which is we start from scratch and then we run the optimization and see what are the best possible spares assortments. But we can also choose to analyze an existing stock solution. So if I select analysis here, and then in the column here called allocation point identifier, I select that point that we just inserted, the one that we said, this is what we bought. So we said we bought all those items, and then I want to analyze this. And if I do it now, I didn't do any other changes, so that point should be exactly the same. So if I zoom in here, you see it's the exact same point, right? It's on top of the other one, so it gives us the exact same availability and exact same cost. So that's a good test. So next step now would be to actually adjust the input to something that we wanted to do the sort of sensitivity analysis for. And let's say that we wanted to increase the failure rates on all items with 10%. Then there is a table called scale factors, which is kind of handy when you want to do this kind of what-if analysis. So here I can give a factor, like a number. So for example, 1.1. So that would be an increase with 10%, right? And it will be applied to all the failure rates of the model. Okay? So that's a very easy way. Of course, I could go to the failure rate table and I could update all the values here with an increase of 10%. But if you just want to do some tests, do some sensitivity analysis, the scale factors table is really handy. So that's an increase of 10%. Click calculate here, save the file, and I get 1 point because it was the analysis type of problem and not optimization. And we see how we ended up here. Okay, so we want to compare that to the original point, which was this one, 566. So what happened? Well, we used that diff line here, and I see that actually it becomes another 10 million more expensive, so going from 285 to 295 million. Again, it's 20 years, so it's a long period, but it's in percentage, it's not that much increase though. Anyway, I also get some lower, actually get lower availability as well, because we have more failures, right? So that's obvious. If we have more failures, we're stopping the systems more often, which means that availability is lower. So how can it be more expensive? Because we're not buying any spares, right? So now I'm going to show you something new that I haven't shown you before. Here is a sort of a list box we can select stuff from. So if I click that one, and so far we've only been looking at the live support cost, which is the total cost model that we've been discussing with both investment in spares and resources and everything, but also the recurring costs, which means typically all transportation and repair costs and reorders and everything. But if I would select only the investments here, and click it. So there we go. It just zoomed out a little bit. So I'm zooming in again. What you see, what happened now, when we only regard the investment costs, they are exactly the same, right? Because we have the same stock solution. I fixed the stock solution. So that means that the investment is the very same. However, we will have, if I look at the depreciation cost instead, or sorry, recurring cost instead, which are the costs occurring each year, you'll see how it moved away to the right. So this means that it was only the recurring cost that differs. Here, this explains the entire difference in the cost addition in this scenario.
Repair.
Yeah, and it's mainly due to repair costs. Exactly. But it can also be costs for consumables or more transportations due to more failures, and it can be we're performing the tasks more times per year, and performing tasks can be expensive, and so on. So there are many aspects of the costs, and then we can use the cost analysis part as well to dig deeper into that. But could be also, another simple example here that can be pretty interesting. So yeah, sure, the failure rates if they increase, but maybe we can get a lower cost. So if I can get a 15% reduction of the costs for this 10% increase of failure rate, is that good or bad? Well, that's kind of hard to answer, but here I can just add the number here, 0.85. So I decrease the unit prices for all items. I run the calculation again, and it turns out that it was not into the entire life support cost. There, and we zoom in a little bit. Actually, it ends up below the curve, but much closer. So still not a super good idea to get this deal. So, okay, but what if we get say we get 25% reduction in the price? Run it again, you get another point, we zoom in, and you see, oh, that's better. That was actually worth it. So I can take, if the prices can go down, if I can negotiate the prices downward with 25%, I can take an increased failure rate or failure tendency with another 10%. So this kind of questions is, as I said, really easy to evaluate when you have the model. And with this scale factor table, there are, as you see, you can vary some other input parameters as well. Here are costs for consumer jet, but you can add costs for actually storing spare parts as well. You can also adjust the turnaround time for the repairs and replacements, the costs and lead times for reorders, PM intervals, transportation times, resource costs. So this is a handy way of doing what-if analysis and so on. Of course, you can always go in and cherry pick some specific items or some specific locations where you want to change something, but on an overall basis and for general what-if analysis, this is really powerful. Okay, I have one more example that I think it's kind of good timing for our schedule, so it should be the last one then. The last one was, so what if, sort of similar, but what if we can lower the turnaround times with 30% for all maintenance, but it will cost us 100 euros for each repair? Is that good or bad? Should we take that into consideration? So see it as a sort of as a contract negotiation. Should we outsource the repairs or should we keep them in-house? So maybe if we do it in-house, we already have the personnel to do those repairs and so on. But if we outsource it, we buy a service from a provider of some kind. But that will of course cost us something. So then we can see if that is cost effective or not. So I close all the files, open up the start file here again, the original one, remember? I run the calculation to get the curve. Just maximizing the windows here. And then we wanted to do a comparison, so I call it with call TAT extra something. Okay. What did I say? I said 30% decrease of turnaround times. So either I can go to the task table and look at it, but here I have so many tasks, so I maybe don't want to have repair tasks for each of the items because it differs in price and things like that. So I think I'll use the scale factors again anyway. Okay, and here we had the maintenance turnaround times, and I said decrease 30%, so we have a factor of 0.7, right? And then that will give us an additional cost of 100 per repair. I realized that since the repair costs are different for all, I just make an increased increased maintenance cost with that depends on what they were, but of course I could have, you see here that I forgot that I had costs already for those, so we have different costs for all the different maintenance activities, but let's just say that we increase with 10% of the maintenance costs, right? So factor 1.1. So do you think this is a good idea or not? Well, let's ask OPUS. We just run the calculation. 3 seconds later, we have an answer. Okay, so this is interesting. What happens now is just you see that the curves, they cross each other here. You see that? So this means that if we are looking for an availability around like 75% or lower, the original alternative is better. So there's no idea to outsource the repairs if we are not interested in higher availability than like 75%. However, if we are striving for a higher availability, upwards 80 or 90% on the, as the fleet readiness here, it turns out that it's actually more expensive to do that with the original scenario compared to this offering that we got from the supplier. So we can actually get here 90% availability compared to, there we go, and just do the cross info there to get the difference between the points. So we can save here, in this case, $10 million over the 20 years if we go for the outsourced repair, if we're looking for 90% availability. So this is how quick it is to actually evaluate different, different alternatives, different suggestions that we have, different decisions that we face, which will, of course, help us save money and increase availability of the fleet. So that's what we want to do. And I can go on. I mean, there are many different scenarios like this, but those are some typical questions that we see that our users around the world, they get this, they have these kind of situations, they want to evaluate these kind of situations, and they want to have decision support because it's impossible to just guess which is better. And like here, in this case, I think it was a pretty good example because we got that cross between the curves, as you see, around 85% availability. So saying that, yeah, for starters, it's not a good idea, but if we aim for the higher availability, it's actually a good idea to take this deal that we are offered. Okay, I think that was the last example that I'd prepared for. So, Jan, would you like to, you often have some good points to make after me, so please.
Any questions?
Yeah, of course, questions. Sorry, I forgot. Thank you.
시간이 없어서 뒤에 슬라이드는 끝까지 못하고 가네요. 지금 어찌됐건 그 부분은 저희들이 지금 요 예제 있죠? 예제 파일을 받아와서 제가 전달하기로 했거든요. 그래서 혹시 저희들한테 이메일하고 뭐 이런 것들이 정확하게 전달이 됐는지 한번 확인해 주시고요. 자료를 받아서 다음 주 중에 제가 전달하도록 하겠습니다. 사실 시간이 없어서 제가 나와서 요약 설명을 안 했어요. 시간이 짧아질 것 같아서 되게 중요한 것들이 되게 많았었는데 뭐 그런 시간이 좀 없었는데 이거는 저희들이 대전이나 서울에서 시습 교육을 하는데 그때 오셔가지고 시습할 때 제가 같이 할 수 있도록 다시 한번 노력을 하겠습니다.